So you've all seen induction, I assume. But when I've given these slides in this class, people have seemed to think that it was useful. All right. So here's the topics. I guess we're focusing on what does it say about the integers and loop invariants, which I'm very passionate about, and recursion I'm passionate about. All right. So first, counting. I downloaded this video. It was a video I saw a billion years ago, in which this little boy asked Grover to count to 1, and Grover thinks about it hard and says 1, and then the kid says, "I love you." So it's a great video. But anyway, it's we need to learn how to count, right? And then here's an algorithm that counts, right? And then you can ask various questions. Right here, we're counting, and we can ask, do you ever reach infinity, right? And the answer is, if you do it in time, no, you never reach infinity, right? You only get to real positive. You only reach positive integers, right, which are all finite. And these call them the natural numbers, and infinity is not 1, right? Everybody get that? Right. So then you can ask, again, do you ever reach all the positive integers? And so you can say, does there exist a time in which you've reached all the integers? And is that true? No, it's not true, right? If you give me any point in time, t is finite, you haven't reached them all, right? I can give you an integer that you haven't gotten to, right? Everybody buy that? All right, but here's a slightly different question. Is every positive integer reached? We got some no's and some yeses, right? Is every positive, right? And here's a different statement. We're saying for every I, there exists a time at which you reach it, right? Everybody see the difference, right? And this is true, right? You give me some positive integer I, right? And as long as I is a nice positive integer, my code will reach it at some point in time, maybe not during our lifetime. Right? Does that make sense? All right. And so these statements are telling us something deep about the positive integers, right? That aren't true about other sets, right? If you've taken 2001, you'll learn that the integers are countable and that the reals are not countable, right? And in fact, this is our definition of the integers being countable, right? All right, so what is induction? Induction is the statement up here, and it's going to, you might say it's something that's intrinsically true, and I'm going to say no, it's an axiom that we're going to add. All right, and so what is it saying? It says, you give me any statement S of I. What's S of I? Is you plug in some integer, and it tells you whether the sentence is true or not for that integer, right? It could be that it will rain on day I, right? That some days it rains, right? We'll put red if it doesn't rain and green if it does rain, right? We could put down the statement S of I says that if you sum the first I numbers, you get this equation, right? We could have S of I be that if you give me a proof of length j less than I, then the proof is valid, right? Or you could say my iterative algorithm works for the first I iterations, right? Or you could say my recursive algorithm works for inputs of size at most I, right? Or you could say my differential equation, right? I can plot it up until time t, right? Or you could say, if you give me a string with at most I characters, then I can parse it using my grammar, right? You could say, given a graph with at most I nodes, if the graph is planar, right, then I can color it with 6 nodes, right? You can say all these statements, right? And what is our goal? Our goal is to prove that S is true for all I, right? And right, S is some weird complicated thing, and there are an infinite number of I's. So how do you possibly prove this, right? And once you have this axiom, you prove it as follows, right? You first prove it's true for 0, and then you prove the statement, right? How do you prove the statement? Is you say, we play the game. We let the adversary give us an arbitrary I, right? And then we have an oracle assure us that S of I minus 1 is true, right? And then we have to prove that S of I is true, right? Everybody get the game? All right. And then after we've done those things, then we've proved the left-hand side, so we can use mode exponents to get the right-hand side. Right? Does that make sense? That's how we use it in a proof. All right. So you might argue, why can you include, why can you conclude this? Well, let's do the intuition, right? The intuition is, right, here we define what we mean by our colors. What is our goal? Our goal is to prove that they're all green, right? How do we do it? Well, you first, right, you assume the left-hand side. So we have some oracle, which is assuring us of the left-hand side, right? So the oracle starts by assuring us that S of 0 is true, right? And then how do I prove S of 1? Well, I give the oracle I equals 1. She says, hey, if S of 0 is true, then S of 1 is true, right? So I know that S of 1 is true, right? And then how do I prove S of 2 is true? Well, I give her I equals 2, and she tells me that F of 1 is true, then F of 2 is true. And I know S of 1 is true, so I know S of 2 is true, right? Everybody follow this, right? And you can do this forever, right? For each positive integer, you give me any positive integer, there's a finite proof of S of 0, right? Is there a finite proof of all S of I's? No, that would require an infinite proof, right? Right? For every I, there's a proof, a time at which you proved S of I, right? All right, so we're going to just assume it's true. And why do we assume it's true? It's because, well, we don't know things about the integers, right? What do we know about our model? 1, 2, 3. We can define 1, 2, 3. How do I know that there's not some infinity in there or some number you never get to, right? Here, by assuming that induction is our model, then we're saying if you go 1, 2, 3, you get to all the numbers, right? So, right, this is kind of the things we've said before, right? Here we parse it, right? Everybody get the game, right? The game is you prove the left-hand side, right? You prove S of 0, you assume that you're given an arbitrary I, you assume S of I minus 1, you prove S of I, and then you say by induction, we know for all of I, right? Everybody good with this? I think you did it in high school. Probably. Everybody do it in high school? No, you didn't. Everybody should have done it in high school. Have you done it somewhere else? All right. So we can do various examples, right? This is a classic one that people do. How do you prove that 1 plus 2 up to I is this? Right? Well, the story goes that Gauss was bad in class and his teacher made him add up the first 100 numbers, and he did it in a few minutes. He said, well, there are the first 100 numbers, reverse them, it's the same numbers backwards. You add this way, you get 101 each way, right? And so the sum is each of these is 101, and this is, and then we have n of them, right? So you get this equation, right? Everybody buy that? All right, so how would you prove it by induction, right? You say, is it true for 0? The left-hand side is, you sum up to 0 is only 0, and the right-hand side is 0, so it's true for 0, right? And then how do you do this? Well, I assume I'm given an arbitrary I. I must prove S of I, right? So I have to prove the sum of this. Well, the sum of this, the first I minus 1, right? So then I ask my oracle, and my oracle says, yeah, that adds up to this. So then I do a little rearrangement, and I get what I want. Right? Everybody buy that? Right? All right. All right. So we still might be confused here. Right. So we could write a computer program which you give it in and it proves S of n. Right? I've sort of implied that already, right? So how would you do that? You're given it, right? You first give a proof of S of 0 like we did, right? There's the proof of F of 0. And then you loop up to n and you give a proof that, hey, if F of 0 is true, then F of 1 is true. If 1 is true, then 2 is true. If 2 is true, 3 is true, right? So there's a finite proof of S of n for every integer n, right? Does everybody kind of get that for what it's worth? All right, so we make it an axiom. Why do we add it as an axiom? Is because if we know, if we say we're working over the integers as we know the integers, then it's not an axiom. It's something that's true, right? But if we don't really know what our model is, right? Here are things that we could define, right? Answering your question, right? Then we might want to, maybe there were some weird things in our weird universe, right? And we want to avoid those weird things. And one way to avoid those weird things is to add this axiom. Right? Everybody good? All right. All right. We all know that you can take the contrapositive of things, right? If A implies B, then not B implies not A, right? So it might be useful to take the contrapositive, right? So you kind of bring this in, right? It says if it's not the case that all the S's are true, right? Then either it's not true for 0, right? Or they exist in I such that it's true for S of I minus 1, but it's not true for S of I. Right? Everybody sort of see that? Yeah. So if they're not all true, right, then either the first one's not true, or if the first one is true, then they might be green for a while, right? But if they're not green forever, then there exists a place where they turn from green to red. Right? Does that make sense? All right. Everybody following that? All right. So here, let me tell you that U and all positive integers are special. All right? How do we prove it? Well, clearly 0 is special, right? All right. Now, I don't like proof by contradiction, but let's pretend they're not all special, right? If they're not all special, then there's the smallest integer that's not special, right? We assume that 0 is special, but they're not all special. So there's some other integer which is the smallest that's not special, right? And I maintain that to have that property, to be the smallest integer that's not special, I claim that that's pretty special, right? And that contradicts it not being special, and hence every number is special. Right? Everybody good with that? There you go. All right. Now, another thing we might want to prove in our logic is that our proof system is sound, right? And what does sound mean? Right? First off, what's a Hilbert proof? We need a Hilbert proof is the sequence of sentences where every sentence is either an axiom or it follows from previous sentences. Right? Everybody know that? You should. And right, so here we say, oh, you've proved this guy and you proved that guy, and we have a rule that hence you can add this to your proof. Right? And now we say a proof system is sound is if a sentence has a proof, right? Here's phi down here has a proof, then it's valid. And what does valid mean? It means in any model in which your axioms are true, right? It's also true, right? Do I say that? And how do we do it? We prove by induction, right? S of I will be the statement that if you have a proof that's of length I or shorter, then and you have a proof of phi of I or shorter, then phi is true or is valid, right? And then well, S of 0 is the empty proof, so that's pretty straightforward. And otherwise, we get this by induction, right? Right, by induction, because we assume that all of these guys are valid. And hence, what's this guy here? Well, either it's an axiom, in which case it's true in every model in which the axioms are true, right? Or what do we need from our rules? We need that if you have a rule that from these things you can add this thing, right? You need the rule that if these two are valid, then this one's valid as well, right? Remember when I was sort of making up a proof system for you guys, and soundness was never maybe in George's world, soundness is hard because you don't know what these things mean, right? But as long as I had meaning, I knew that my rules were sound. Right? Everybody good?